Hi dear students of class 1 medical, non-medical, respected teachers and dear friends. In this video I am going to discuss about Newton's formula for velocity of sound in air or gaseous medium and how it was corrected by Laplace. So we will also discuss Laplace's correction to this formula. Since velocity of sound in any medium, solid, liquid or gas in general, V is given by V is equal to under root E by rho, where E is called modulus of velocity and rho is called density of the medium. According to Newton, when sound propagates through air or gaseous medium, temperature doesn't change. That is, temperature remains constant. In other words, the process is said to be isothermal process. So he derived this formula for velocity of sound in air or gaseous medium under isothermal conditions. So according to Newton, under isothermal conditions, PV is equal to constant. P the pressure, V the volume. Then differentiating this equation, we have P first function, derivative second P dV plus second function V derivative of first dP. So P dV plus V dP is equal to 0, derivative constant is 0. Or P dV is equal to minus V dP, or P is equal to minus V dP upon dV, or P is equal to minus dP, or this can be dV upon V in the denominator, so which is nothing but stress over volumetric strain. So by definition it is nothing but modulus of velocity. So it means P is equal to E under isothermal conditions. It means modulus of velocity E under isothermal conditions is equal to pressure of the gas. So therefore, from equation 1, formula becomes V is equal to under root P by rho. P the pressure, rho the density. So which is required Newton's formula for velocity of sound in air or gaseous medium. But at normal temperature pressure at NTP, if we calculate the value of velocity from this, taking pressure as atmospheric pressure 76 centimeter mercury column, density of dry air, and the velocity comes out to be 280 meter per second only, but practically velocity of sound is found to be 332 meter per second at NTP. So it means there is so much error, which is about 16%. So it means this formula needs to be corrected. So this formula was corrected by Laplace. According to Laplace, when sound propagates through air or gaseous medium, temperature doesn't remain constant, and hence the process is adiabatic. So he derived the formula for velocity of sound under adiabatic conditions. So under adiabatic conditions, according to Laplace, PV raised to power gamma must be equal to constant, which is nothing but adiabatic gas equation. So PV is equal to constant is an ideal gas equation. So PV raised to gamma is equal to constant, adiabatic gas equation where gamma is equal to Cp upon Cv. Its value is 1.4 for dry air. Differentiate this equation, we have P first function derivative second means gamma V raised to gamma minus 1 dV plus second function as such V raised to gamma differentiation of first dP is equal to 0. That is P gamma V raised to gamma minus 1 dV plus V raised to gamma dP is equal to 0. Or P gamma V raised to gamma minus 1 dV is equal to minus V raised to gamma dP. Or gamma P is equal to minus V raised to gamma dP, V raised to gamma minus 1 over dP. So V raised to gamma minus 1, V raised to gamma minus 1 cancels, only V remains. So this can be as gamma P is equal to minus dP upon V, which again stress over volume strain. It means it is equal to modulus of velocity. So under adiabatic conditions, modulus of velocity is equal to gamma times the pressure of the gas. For dry air, gamma is equal to 1.4, and if you calculate the velocity of sound using this Laplace's corrected formula, it comes out to be 331.9 meter per second, which is very close to the practical value. So this means this is corrected formula for velocity of sound known as Laplace's corrected formula for velocity of sound in air or gaseous medium. So from this we can find upon what factors velocity of sound in air or gaseous medium depends. Number 1, effect of density. Since velocity of sound is not equal to square root of density, It means more the density, less is the velocity, and vice versa. So that's why sound travels faster in hydrogen than in oxygen. So velocity of sound in hydrogen is equal to 4 times the velocity of light. Velocity of sound in hydrogen is equal to 4 times the velocity of sound in oxygen, which is due to effect of density. Then effect of humidity or moisture. So since density of water vapors is less than that of dry air, so in the presence of moisture or humidity, density of air decreases. If density decreases, velocity increases. That's why sound travels faster on a humid or moisture day than on a dry day. So in the presence of moisture, velocity of sound increases. Effect of temperature. So from V is equal to under gamma P by rho, multiply and divide by V. So PV is equal to RT by ideal gas equation. So it is gamma RT upon M. P into V is equal to M. Density into volume equal to mass. Or molecular weight we can say. Or as RT upon M is constant, so V is directly proportional to for a given gas or air. So V is directly proportional to square root of temperature on Kelvin scale. So velocity of very important factor. Velocity of sound depends upon temperature. So velocity of sound in air or gaseous medium is directly proportional to square root of the absolute temperature. So that's why velocity of sound is more on a hot day than on a cold day. Then if we calculate temperature coefficient of velocity of sound, that is how much velocity of sound increases when temperature rises by 1 degree, 1 Kelvin. So this temperature, if we calculate, comes out to be Vt minus V naught upon T is equal to 0.61 meter per second per Kelvin. So it means temperature coefficient of velocity of sound is equal to 0.61 meter per second per Kelvin. So velocity of sound increases by 0.61 meter per second when temperature rises by 1 degree. So if temperature rises by 10 degrees, it will be 6.1, increase in velocity will be 6.1 meter per second. So that's why velocity of sound is more on a hot day than on a cold day. This is the reason. Then effect of pressure. Now as pressure increases, gamma is constant, density also increases. So it means ratio P upon rho ratio will be the same. Or you can say V depends only upon T because gamma M is constant. So therefore, velocity of sound is independent of pressure, provided temperature is kept constant because it depends upon temperature. Wind velocity. Velocity of sound is also dependent on wind velocity. So when sound is traveling in the same direction as the wind, so it increases, and in opposite direction decreases because wind velocity adds to the velocity of sound in the same direction and it is subtracted in the opposite direction. So wind velocity also affects the velocity of sound. Then amplitude. Velocity of sound is also independent of amplitude provided amplitude is small. If amplitude is large, it increases slightly, almost independent on the average. Velocity of sound is also independent of frequency and wavelength of the wave because V is equal to u lambda. If nu increases, lambda decreases, so V remain the same. So this is all about Newton's formula for velocity of sound in air or gaseous medium and Laplace's correction and upon what factors velocity of sound depends. So till next video, stay tuned, be happy, all the best, good luck.